Hello and welcome to today's training course on moving loads in space gas. I'd like to start by just showing a few real models that are currently using the moving loads module in space gas. And I'll just start with a 10 span bridge, which is a prominent bridge in Melbourne that's currently being upgraded by SMEC to increase its capacity. So I'm not going to go into a lot of detail with it, but I'll just go up here and just show you the moving loads. And when we do that, you can see all of the different scenarios, which I'll explain later, but there's some T44 loads, some UDL loads and some M1600 loads. So I'll just turn some of those off just so that we don't have too much congestion, and maybe just turn on the M1600s. And then you can change the animation speed and various other things, but we'll just click OK. And it may be a little bit hard to see, but if I just zoom in, you can see the vehicles traveling along the bridge. So if I just go into the moving load module, you can see all of the loads that have been set up. And if we double click on one of them, you can see the details of the vehicle. So that's just one of the M1600 vehicles and the path that it's traveling along. So that's the travel path for that particular vehicle. So I'll just load up another job. This is another bridge. This is a new proposed 6-lane bridge over the Ganga River in Patna in India. It's just one component of an overall 9.8 kilometre bridge. So it's currently being designed, and the aim is to have it, well, construction begin in about 2 years. And if I move to a wireframe view and just show the moving loads again, you can see them moving there in 2 directions. So this one's using some of the Indian 70R vehicles, which are a heavy 100-ton vehicle that occupy, well, when you're designing it, they're designed to occupy 2 lanes. So you can only, so even though it's a 6-lane bridge, we've only got 4 lanes of the 70R vehicles. Another common use of the moving loads module is a crane in a building. So in this case, we've got a portal frame building with a runway beam running down each side, and then an overhead travelling crane with a 10-ton hoist. So again, I'll just show the moving loads. So this time we've got 2 scenarios here. We've got one with the hoist at mid-span, so the load will be equally placed on each side of the building, and the other one with the hoist at the right-hand end, so the right-hand side will get more of the load. So it's not quite as spectacular as the bridge example, but you can see the wheels of the trolley of the crane moving down the runway beams. So just having a look at those loads. If I double click on one of these and just have a look at the load, it's just 2 wheels, each one having a 40 kilonewton load on it. And that's on each side of the building. And finally, I'll just show another structure which is a fairly novel use of the moving loads module. It's an abattoir that was designed by MPN Consulting, and basically the moving loads have been used to show carcasses moving along a rail through the building. So you can see some of them moving there, and there's another one coming around here as well. So each one of those wheels actually represents, if I click on here and go into here, you can see each one represents what they've called a cow. So that's a fairly unusual application, but works quite nicely with the moving load module. Another common application of the moving load module would be material moving along a conveyor structure. So now I'll just go into a little bit more detail and just show you how you can model your moving loads. And I'll pick a structure that's ready to go. So you can see it's a portal frame building or a single span building with a crane rail down each side. And let's assume that we want to run an overhead travelling crane along those rails. So the first thing I would do is just go into the moving load module using this button here, and then just create a scenario and give it a name. So let's call it something like that. So let's say this one's got the hoist at the center. And really what the moving load module does is simply create a number of load cases that represent the moving load at various snapshots in time. And so in the next field here you just need to specify the starting load case in that series. So let's say 100. And the time interval between snapshots. So normally you can leave that at 1 second, and then once we introduce the loads onto the scenario, we can specify the speed, which then combined with the time interval determines how far apart each snapshot is in terms of distance. So let's leave it at that and click OK. And then the next step is to add some loads to that scenario. So let's click the Add Load button. There are two types of loads. You can have a vehicle load, which is typically a wheeled vehicle, or you can have a pressure load, which is generally speaking reserved for UDL lane loads on bridges. So in this case we're talking about a wheeled vehicle. If we've already got some vehicles in this model, we can click on this first button here to see what they are and maybe reuse one of them. Or we could go to a library, because there's a standard sets of libraries for vehicles that come with Space Gas. So we've got libraries for Australia, India and the US, and then you can create your own custom libraries, and that train one there is a custom one that we've added. You can see by the slightly different color of it. But in this case we won't use a library, we'll just create one from scratch. So in order to do that we can just click this button here and then basically just type in the coordinates of the wheels and the load that's applied to them. So when you're defining the position of wheels, the X position is the distance from the front of the vehicle. So if the first wheel is at the front, we'll give it an X of 0. In this case you can see here Y is vertical, and so the two plan dimensions are X and Z. So if the wheel is along the center line of the vehicle, then it will have a Z coordinate of 0. And let's give it a vertical load of -25 kilonewtons. So that's just one load in the trolley of the crane on one side of the building. So 4 of those would give us 100 kilonewtons, which is basically our 10 tons. So the next one, let's say it's 3.2 meters behind the first wheel, 25 kilonewtons again. And you can see the wheels appear graphically in the window above. So if you click on one of these lines, you can see that the wheel that applies to that line gets highlighted in red. So generally speaking, for overhead travelling cranes you'll also get some horizontal loads due to braking and acceleration forces. So they would go in the FX columns and the FZ, and also because the horizontal loads are assumed to be slightly above the point where the wheel contacts the runway beam, you may also get some moments coming into play, and so you could possibly have an MX moment, which is a moment about the longitudinal axis of the crane trolley. But in this case we won't worry about that. We'll just click OK and use that as our load. The next thing we have to do is tell it where the load is going to travel. So this is the next section down here, the travel path. So again, if you've already defined some travel paths, you can click on this button, and if there had been some, you could just choose one of those, or we can just create one from scratch. So travel paths can be defined just by node numbers, or by coordinates, or by a combination of both. So for example, if you've got a travel path that goes between two particular nodes and you want to move it or offset it away from those nodes by a certain amount, then you could also put in a coordinate which represents the offset. So let's select the travel path graphically, and in this case we just want to go down the left side of the building. Just zoom in a little bit. So from here to here, and you can see the two node numbers appear in the table up there. It's probably a good idea to give it a name at this stage as well, so let's call it the left rail, or left side, and then click OK. Further down in this form we've got a start position, so if the vehicle starts at the beginning of the travel path, then that will be 0. In this case it does. The speed of the vehicle, so you can see up here that, as I mentioned earlier, the time interval for this scenario is 1 second, and so if we use a speed of 1 meter per second, then we're going to get a load case that represents the vehicle at every 1 meter distance along that travel path. So the speed combined with the time interval is just used to calculate the distance between load cases, and doesn't have any effect on any sort of dynamic factors or anything like that. The delay is handy if you've got vehicles that follow each other, so you might start a vehicle at time 0 and then start another vehicle maybe 10 seconds later so that it follows the first one. In this case we'll leave it at 0. The load factor is handy if you want to factor up your loads at this stage, otherwise you can do that later. The lane factor is just for bridges, and the dynamic factor adds a dynamic load allowance due to the speed of the vehicle. So let's in this case assume that the dynamic load allowance is 0.3, and so the factor will be 1.3. So then we click OK, and you can see that vehicle now appears in the tree on the left hand side. It's unnamed, so let's just double click on that and go back, edit the vehicle and just give it a name. Just makes it easier to understand what we're doing. So that's the left hand side. Now let's just do the same thing for the right hand side, and we can use a copy facility. So I've just right clicked on that first load and I can choose copy and then choose paste, and then if I go and double click on that to edit it, so the vehicle is the same, so I'm not going to touch that, but the travel path is now different. So I need to click on the right hand side of here for a new travel path, and this time I'll choose the right hand side of the building. And I'll just go back in there and give it a name. And then everything else is the same. So the only thing we need to change here is the dynamic factor 1.3 again, and then click OK. By the way, to copy that load I could have just held down the control key and dragged up to the scenario, and I would have been able to do a copy that way as well instead of copy and paste. And in order to delete something, you can just right click on it and choose delete, or just hit the delete button if you want to. So we've got our two vehicle loads on the left hand side and the right hand side, and the next thing I would probably do is just view them. So there's a view button over here. We can view the travel paths or the loads. And as you can see, they're traveling along beautifully between the two nodes that we selected for the travel paths, and I'll just show that again, but they're a bit too low because they're below the top of the crane, or below the top of the runway beam. So let's just change that by double clicking on each one again, editing the travel path, and just increasing the height of the travel path by the height of that runway beam plus half the height of the bracket that's holding it. And then the same for the right hand side. So in this case we're using a combination of nodes to define the travel path and an offset away from the line that joins those nodes. So now when we view the diagram, we'll view the loads again. This time they're up on top of the runway beams. So that vertical positioning doesn't affect anything as far as the load generation goes, but it just makes it nicer to look at when you're viewing it graphically. So we've defined the vehicles and where they go, but we haven't actually told it which members are going to be loaded by the vehicle wheels. So you might think that's obvious, but we do actually have to tell it which members are being loaded by those wheels, because if we click generate at this stage, because we haven't selected any elements to load, we get a warning message just to tell us to do that first. So we'll choose the select elements to load button, and then we just need to select the members that are loaded directly by the crane wheels. So it's important not to select any other members that aren't directly loaded by the wheels, because otherwise they could get loaded incorrectly. And then I just right click and click OK, and then click generate. So that then goes ahead and generates all of the loads for that scenario. And then if we just turn the loads on graphically and just scroll through them using the page up and down keys, you can see the concentrated loads moving along those two crane rails. Just to illustrate what happens if you don't select the members that the wheels are loading, so if I just go back in and maybe just deselect a couple along here and then generate again, this time you can see there's a gap there in the loads, and if I scroll through them, you can see that there's nothing happening in this section here where I didn't select the members. So even though in the moving load generator, if you view the loads, it looks like they're being loaded all the way along, but because you haven't selected them, they won't attract any load. So you just need to be very careful of that. So let's just select them again. And while I'm in here, I'm now going to also combine these moving loads with some of the non-moving loads, such as dead load and live load. So a series of moving loads in this particular case generates load cases 100 to 133. So that's 34 load cases, and it works that out automatically. And in order to combine those with non-moving loads, we need to generate another series of load cases, which are basically a combination of these primary load cases combined with the non-moving load cases. So just to illustrate that, I'll just close this briefly, and if we look at the load cases we've got a dead load and a live load, and then all of the moving loads. So in order to combine those, let's first of all create a combination of the dead and live loads. Let's call it load case 11. So that load case now appears in our list just the same as any other load case. And then in the moving loads module, one of the properties of the scenario, and I'll just click on the scenario heading, is to combine all of these load cases, the ones that start at 100 and finish at 133, factored by a certain amount. So let's factor them by 1.5, and then combine them with load case 11 factored by 1, because load case 11 has already been factored to ultimate, so we don't want to further factor it up. And let's start this series of load cases at, let's say, 200. And then if we generate those, we've got the dead load, live load, and the combined load. And then from 100 up to 133, we've got the moving loads on their own. And then from 200 to 233, we've got the moving loads combined with the dead and the live load. And you can also see that if you look at the combination load cases, you can see there the load case that we just input, combining dead and live. And then these are all the combination load cases that combine that load case 11, which is factored by 1, with all of the moving load cases that are represented horizontally out there, factored by 1.5. And they continue. If I widened this out, you'd see more of those 1.5s. So let's assume that's all we want to do. We could then just go ahead and analyze that. And then just have a quick look at the results. So looking at deflections, I'll just go to a single load case to start with. Let's go to one of the combination load cases and turn off the annotation, expand the deflections a little bit, and then I'll just scroll through a few of them. So they all look pretty similar. Let's just create a filter of the two runway beams, and I can do that rather than just selecting them member by member. I can click on the section and material properties tab here and just choose the section that corresponds to those runway beams, and then come in here, right click, and then choose create filter from selection, and we'll just give that a name. This will just help us to have a look at the loads a bit more clearly just on those beams. And then look at the deflections. There's a little bit of horizontal deflection going on there as well because the building's deflecting horizontally. But if we just look at it maybe from side on and turn the loads on as well, you can see there's most of the deflection occurs where the load is. And then if I scroll through them a little bit, you can see that deflection is reflected in the position of the load. Similarly with bending moment diagrams, just scrolling backwards now, you can see they change according to where the load is. And we could show all of the combination load cases if we wanted to, just by choosing a selection, let's say 200 to 233, and so you get a lot of information there. And probably at this stage I'd turn on an envelope just so that you get the minimums and maximums, something like that, and maybe turn the labeling on. And so from there you could proceed to do a steel member design or a steel connection design just on those load cases, just the same as any other load cases that you might have input manually. Before I get off this model, I just want to go back into the moving loads generator and just show you how to generate a second scenario. So let's add a scenario, and this one we'll call the same as before, but the hoist, let's say at the right side. And so we'll start the series of load cases from 300, and time interval again 1. Now I should be able to just copy my loads down, just holding down the control key so that I'm adding the load to that scenario. And instead of copying the right hand side trolley, I'm just going to use a different method just so that I can demonstrate how else you can do it. So I could just click the add load button, and then because I'm using a vehicle that's previously been used, I can click this button and just select it. There's only one vehicle, so select. And similarly with the travel path, I've already got a travel path for the right hand side, so I can select that. And so that's another alternative way of generating or reusing the vehicle and travel paths that we've already got. So they're a little bit like section properties. If you've already defined a certain vehicle or a certain travel path, you don't redefine it multiple times, you just keep reusing it. So because we want this crane to apply to the case where the hoist is close to the right hand side of the building, we just need to go back in and just change the load factors a little bit. So let's say the one on the left is only getting 10% of the hoist load, and the one on the right is getting 90% of the hoist load. Actually, that should be 190%, shouldn't it? Because it's getting its own load plus the load that's been reduced from the left hand side, so 1.9 is the load factor. And then we could generate that again and create all of the loads for these two scenarios. By the way, if you notice here, we've got little checkboxes here that allow you to turn scenarios off. So if I'm only interested in the loads on the right hand side, I could untick the one on the left hand or the one on the center, and then when I hit generate, it will only do the ones that the scenarios that have been ticked. So if I turn, well, let's just have a look at the loads, and I'll scroll through them so you can see the other loads have now disappeared because we unticked them, and then just scroll through them. And this time you can see that the load on the left hand side is fairly minimal, and the load on the right hand side is getting almost the full 10 tons. The next thing I want to do is just move on to a simple bridge structure and just show you how the moving loads module can be used to generate your vehicle loads on a bridge. So let's just open a job. So it's a small 40 meter long 3-span bridge, sorry, 3-lane bridge with 2 spans. There's the supports. It's made of super T-beam cross sections and some internal diaphragms, which I'll just turn the transparency down a bit just so you can see them. So you can see them across there. And basically we just want to generate the moving loads for this small bridge. So last time I showed how, in order to select which members are going to be loaded by the moving loads, we selected it, or we clicked a button inside the moving load generator and then selected them graphically. But you can also do them at this stage before you even start generating any moving loads, just by in this case I'll select the sections and materials tab, choose the section that corresponds to the longitudinal members. So that's just the same as if I had selected them, you know, just using the mouse. And then I can go into the moving loads module and generate my data as before. So because it's a 3-lane bridge, I'm going to create a couple of different scenarios, and let's start with the first one, having the heaviest vehicle in the outside lane. So I'll leave the starting load case as 101 and the time interval at 1 second again, and just click OK. So because I selected those beams before I even got into this module, if I click the Select Elements to Load button, you can see that they've already been selected. So that just shows that you can skip that step if you do it initially. So let's add our loads again. So I'll click the Add Load button. And this time, because it's a standard bridge, I'm going to go to one of the standard libraries, and I'll pick on the Australian library and just use one of the standard M1600 moving load vehicles. So it's been selected here, and you can see the library name in brackets that it came from. And then let's define the travel path. We'll call this the left-hand lane, or left lane. And I'll select it graphically just based on the very left-hand edge of the structure, and then I'll give it an offset so that it's not right on the edge, and in this case I want 2.8 meters at both ends, so that moves it into the position of the first lane, and then I'll click OK. So again, I'll leave the start position at 0, meaning the vehicle starts at the beginning of the travel path. The speed can be 1 meter per second. So again, combined with the time interval of 1 second, we're going to get a load case for every 1 meter of movement of the vehicle. Delay of 0. The load factor, I'll leave at 1 again. The lane factor, this is the left-hand lane, and let's say the heaviest vehicle is going to be in that lane. I'll leave that at 1. And the dynamic factor, assuming a dynamic load allowance of 0.3 again, that means I need a factor of 1.3. So we could view that load quickly just to make sure it's going in the right direction and in the right position. So there it goes. And then, as we did before, because I'm using the same vehicle in the other lanes, I'm just going to copy that one. So I'm going to drag it up to the scenario and hold the Control key down, and do that again to get our 3 lanes. Now, before we can change them into their correct lanes, I'll just show you the tool we've got here for generating load or generating lanes on bridges. So we click the Generate Extra Lanes or Extra Travel Paths button, and then Generate Lanes. So this just allows you to start with an existing lane, which is what we've already defined, and we want 2 extra lanes spaced at 3.2 meters apart to the right of the first one, and we might as well copy the loads as well. Actually, that means I didn't have to do that here, so let's just delete these. Go back to where we were. So we'll generate the extra lanes, and if I tick copy loads, then that will take care of the vehicles being copied as well. So now if I view those, you can see we've got all 3 lanes now set up. By the way, if you want to stop the animation, just hit the escape key and that'll take you out of it. So now I just need to double click these and just change the travel path names to what they really are. And we also need to change the load factors of these lanes, because we're assuming that the heavy vehicle is in the left-hand lane. fact, let's just change the name of that scenario. So heavy vehicle in left lane. So that one's got a lane factor of 1. And as you know, when you go to the other lanes, the factors go down to 0.8 for the next one. And then 0.4 for the other lanes. So now let's just create another scenario, this time with the heavy vehicle in the center lane. So we'll add a scenario. And this will use the next sequence of load cases, so from 201 onwards. And we can just copy these down just by dragging them. So you drag them onto the scenario that you want to put them into. And the only thing we need to do now is just double click on each of these and change their lane factor. So in this case it's 0.8 for the left, 1 for the center, and 0.4 for the right hand side, as we've already got. Now when we view the vehicles, you can see we've got the two scenarios and we can show them both, which is a little bit pointless because they're just going to be on top of each other. So let's just turn one of them off and just have a look at the other one. So they're color coded. You can see these are purple and the other ones are red. By the way, the travel paths can be any direction. They don't have to be in the longitudinal or transverse direction of the structure. They can be at any diagonal or around a curve even. So for example, if I just go back into the travel path, you can see you can give it a radius, so you can follow a curved travel path as well. Just before I generate the loads, another couple of buttons that are in this form are the vehicles button. So that just allows, if we had more than one vehicle, you'd see them listed here, and you can double click on them or just click the edit button to get into their data and modify them or whatever. There's also the travel paths button. So you can see we've got 3 travel paths, and so you can just double click on one and edit it or do what you like to it, rather than have to go back to this tree all the time. The next thing I want to do is add some uniformly distributed lane loads to these scenarios. And so going back to scenario 1 with the heavy vehicle in the left lane, we'll add another load, and this time instead of a vehicle I'm going to choose a pressure. So again, if you had previous pressures here, you could click that button to select them and view them. Otherwise we just click here to add a new one. So this is a UDL. It goes with an M1600 load, so it's 6 kilonewtons per meter over a 3.2 meter lane width. And you can specify the length of the pressure here. So let's make it 25 meters, or roughly the same as the M1600 vehicle length. And then the next field down here is the load spacing. So although this is a uniform pressure acting over an area of 25 meters long by 3.2 meters wide, Space Gas actually approximates that by a whole series of point loads, and the spacing of the point loads is what you specify here. So if you want more accuracy, then you could give it a smaller spacing, or if you're not too worried about it, you could give it a larger spacing. So the larger the spacing, the less point loads will be generated. And then finally down here we need to specify the pressure. So we've got 6 kilonewtons per meter acting over a 3.2 meter width, which equates to 19.2 kPa in the negative vertical direction. The next thing we do is select one of the existing travel paths that we defined earlier. So let's put this one in the left lane and then click OK. Now we can simply copy that one like we did before, just by dragging it up to the scenario while we're holding down the control key, and we'll do that twice, one for each lane. And then we just go in and change the, first of all, the travel path to the one we want. So in this case the center lane, and then also the lane factor, because in this case we're the heavy vehicle in the left lane, so we want this to have a load factor of 0.8. And then we do the same with the last one. Change to the travel path we want, and then change the load factor. So now if we view the loads again, and I'll just look in that first scenario, now you can see that we've also got a pressure that's moving with the vehicle. So the pressures can be moving or stationary, and the speed of the pressure doesn't need to be the same as the speed of the vehicle, although most times it would. But to generate, let's say, a stationary pressure instead of a moving one, all we need to do is specify the speed as 0 and then just give it a start position. So let's say it starts at 25 meters, and we'll view that. So there's that pressure on the left hand side that's stationary and positioned 25 meters along the bridge. If you want the pressure to be the full length of the bridge, then rather than specify the length in the start position, we can make that 0, and in the pressure we can just edit that and just make the length 0. So this is just a warning saying that because I'm changing this pressure, it's going to affect the other loads that also reference that same pressure. So let's say that that's okay in this case. So I've given it a pressure length of 0, and because the speed is also 0, the program knows that we want to apply that stationary pressure over the full travel path length. And so if we view the loads again, just for that first scenario again, now you can see all 3 lanes have got that stationary pressure acting over the full length of the travel path. Just one other thing on the stationary pressures. You've also got an option of generating the stationary pressure just in the starting load case or in all load cases. So looking at this scenario with the heavy vehicle in the left lane, we're going to get 79 load cases from 101 to 179. And if we generate that stationary pressure in all 79 of those load cases, we're going to be duplicating those loads, which means that we can save ourselves having to create another combination load case to combine them with the moving loads. But the downside is that we generate a whole lot of extra loads that sort of clog up the program a little bit, or slow down the analysis anyway a little bit. So for that reason you get a choice of generating the stationary loads just in the starting load case. So let's do that. We'll generate the loads, and I'm not going to generate stationary loads or uniformly distributed loads in the second scenario because you already know how to do that. Just follow the same procedure. So we'll generate the loads. And if we just look at the loads, you can see we've got our primary load cases here. We've got a self-weight. These were already defined when I opened the job. A superimposed dead load, a barrier self-weight, also a combination of those 3 load cases, so 1.2 times the self-weight plus 2 times the superimposed dead load, plus 1.2 times the barrier dead load. And then we've also got the stationary load, which I was mentioning before is only generated in the first load case. So in order to combine that stationary load with all of these other moving loads, we need to create some combination load cases. So let's just go into the combination load cases, and you can see that one is already there, combining the dead loads and live loads. So let's just add the stationary UDL as well. So we'll give that a factor of 1.8 and just add to the title. And then we'll go back into the moving loads module, and as I showed before with the overhead travelling crane, we'll now combine all of these moving loads with those static loads. So we want to factor the moving loads by 1.8, combine them with load case 11. So load case 11 is that one that's got the dead load, superimposed dead load, live load and stationary load in it. And we'll use a load factor of 1 because they've already been factored up to ultimate. And this series of load cases will start at 301. So I'm only doing this for scenario 1. I would also need to do it for scenario 2, but the procedure is the same, so I won't bother with it. Generate the loads. And now we'll just have a quick look at the load cases that have been generated. So we've got the 3 basic load cases that we started with, the combination that combines those, and the stationary. Then we've got the moving loads, which are just the vehicle loads with the wheels. And then further down, vehicle loads for scenario 2. So this is the heavy vehicle in the center lane. And then further down, starting at 300, we've got the heavy vehicle in the left lane combined with load case 11. So that combines it with the dead load, live load and stationary load. And so if I look at the combination load cases, and I'll just widen this out again a little bit. Just let me go back into that. Right, so load case 11 is the combination of these 3, and then all of these other load cases are load case 11 combined with the moving load cases factored by 1.8. I'm not sure I've stated that all too clearly, but if that doesn't make sense, just email us or ask us a question on the Q&A and we'll be able to clarify it a bit better. So as with the building with the overhead travelling crane, we can now analyse the job. You can see that the moving load generator can generate lots of load cases very quickly, so you've got to make sure that you don't have your time interval too small so that you get loads too close together and you're unnecessarily creating load cases that you may not need. So just going to wireframe mode and having a look at the bending moment diagrams. So that's load cases 101 to 179. So they're all the load cases that correspond to the heaviest vehicle in the left-hand lane. And you can see that because the bending moment diagram increases as you go towards the left. And then if we select the load cases for the heaviest vehicle in the center lane, that's those. And then if you look at the load cases that correspond to the combination of the heaviest vehicle in the center lane combined with the dead load, live load and stationary load. That's those. So they're obviously a much higher magnitude because they've got the other non-moving loads combined with them. And then of course you can get a moment envelope if you want. So I've chosen absolute maximums there, that's why that peak is going down instead of where it was going up before. So if I choose both instead, now you can see it's an envelope of what we had before when we had all of the load cases shown individually. And then if you want to turn on the values, you can. And then go ahead and design just as you would normally. I just want to show another structure. This is another bridge, a skew bridge. So this is simpler again. So just looking at it in plan, if you've got a skew bridge, something like this, and let's say we want to generate some loads, I'm just going to put one lane down the middle. So we'll add a load, and let's this time just choose a T44 load, and the travel path, which we'll select graphically, can just go from here to here. Then if we view the, well, we need to first of all select the members to be loaded, so I'll do that. So I'll select them all. And if we view the loads, and I'll just slow them down a little bit. You'll be able to see that when we get to the end of the travel path, and I can hit the space bar just to pause it, you can see that this wheel here is off the structure, even though it hasn't quite reached the end of the travel path yet, because the end of the travel path is there. Just zoom in a bit. And so it's still considered to be active, and its load will be transferred onto this member here. Whereas in reality, that load wouldn't go onto the bridge at all. And so we've got another facility where you can specify a loading area so that you can limit any wheels that fall outside that load area to be ineffective. And the same thing really happens at the start of the travel path as well. So the way that works is that if you tick the ignore loads that are outside the loading area option and then select the loading area, it's just a matter of creating a polygon around the perimeter of your structure. So the coordinates of it are shown there. And then even though it'll still look the same when you view it, when you actually generate the loads, once any wheel falls outside of that loading area, it will become ineffective and just be ignored. A couple of the other things to explain in here as well is the option here for applying member loads to the closest member only. And if that option's unticked and I hit the generate button, and then just have a look at the loads that are generated, just scroll through them a little bit, and I'll change the transparency of the members just so the loads show up a bit better. You can see that the loads are sort of a little bit random, and they increase and decrease depending on what load case we're in. And the reason for that is that each wheel, if it falls in between two members or not right on a member, it gets distributed in inverse proportion to the distance from each member. And so a load that falls, let's say, inside this area here would be distributed onto all four of these members. And so a single wheel could generate 4 loads on 4 different members. On the other hand, if you don't quite need that much accuracy, you can tick the apply member loads to closest member only option. And in that case, for each wheel, you'll only get 1 load. So now if I scroll through them again, now you can see that they represent a bit more closely the actual wheels. So the distribution is not quite as accurate, but it's probably accurate enough for most jobs. Another option that you need to be aware of is the check vertical proximity option and the associated proximity distance field. And this is useful if you've got multi-layer structures. Say for example you might have 2 bridge decks, one running above another, and each one's got different moving loads on it. And so that you don't get those mixed together, the moving loads that are within this distance here that you specify in a vertical direction of a member that's selected for loading could get some of that wheel load. And any members that are further away than that distance in a vertical direction won't be getting any of the loading from that wheel. So just to demonstrate, if I just copy this structure so I'll just make another copy of it, let's say 5 meters in the vertical direction. So now we've got 2 of those. So I want to generate loads on both of them, but I want a different scenario for each level. So I select them all because I want to load all of the members. And for this one, I'll just check the travel path. So that's the one on the lower level. So let's change the scenario name to reflect that. Actually, let's just change that back because I don't really need to do that. I was going to create a separate scenario for each level, but I can just create a separate vehicle for each level. So let's just copy that vehicle. And then for the second vehicle, I'll change the travel path. Call it path 2. And this time I'm going to choose the upper level. So now when I view the loads, let's have a look. I've actually changed them both, so let's just put that one back to travel path 1. I'm going to have to create travel path 1 again. Looks like I've somehow deleted it. So travel path 1 is the lower level. Right, so we'll view the loads quickly. They look okay. And just so that I can demonstrate this properly, I'm going to reverse the direction of the second travel path. So I'll change the node numbers to the reverse direction. Apologies if this is getting too complicated, but you'll be able to see what I'm doing in a minute. So now we've got them going in reverse directions, just so that you can see that the loads on each level are completely different. Now if we generate the loads with this option turned off, then because the two sets of loads are vertically above each other, they'll be shared on the two different levels. So if I generate the loads, and then just scroll through them, you can see that we're just getting all the loads on the bottom level combined from the two levels. Whereas if I turn that proximity distance on, and 1 meter is enough because the two levels are 5 meters apart, so anything less than 5 meters would work, and generate again. And then scroll through them again. Now you can see that they're kept separate because they're only being applied to members that are 1 meter vertically from the wheel. That took a while, but we got there. Finally, I just want to show that you can now also generate loads on plate elements, which is something that you couldn't do in earlier versions of the moving load module. So I'll just quickly draw a rectangular plate. And then I'll mesh that down to elements that are, let's say, 1 meter in size. Turn on the gaps so that you can see the elements. And then we'll just do the same as before. So I'll select all of those plates, choose the moving load module, give it a scenario name, add a load. Doesn't really matter what load because I'm just showing here how you can load plates now. So an M1600 travel path, we'll do it graphically again. And then just have a look at the loads just to make sure they're going in the right position. They look fine. And then generate the loads. So the difference with plate elements is that a plate will get loaded only if a wheel falls somewhere within the plate. So if a plate doesn't have a wheel on it, then it doesn't attract any load. Now if we just look at the loads and scroll through them again, and I'll just turn the transparency down a bit so that you can see it more clearly. And then I'm just using the page down key to scroll through the load cases, and you can see now that we're getting loads applied to the plates, or applied to the plate nodes. Previously you had to draw members with the plates, and the members attracted the loads which then transferred onto the plates, but that's no longer required. So that's all I wanted to show, and I hope that gives you a good insight into how the moving load module in SpaceGASS works.